week of the series of lectures on dynamic auction by Zaifu. And today we have morning session and afternoon session. And afternoon session start with 3:30 in the same room. Okay, the floor is yours.
Okay, yeah, thank you. Thank you for coming. I realize because now it's very close to the end of the semester, so it's very difficult to have you here. I really appreciate your coming. Okay, so in the third lecture, I'm going to present actually recent work just published by MOR with Professor Fujishiki. So as probably most of you already know the work of Baldwin Crumpery, and now we are going to present an option paper in which all agents will have a common unimodular demand type, but agents have private information and can be strategic. So now we design a dynamic auction which can always converge to a competitive equilibrium and actually also generate VCG outcome. And more importantly, we can prove that sincere bidding will be exposed perfect Nash equilibrium. So here, let me briefly introduce what is the problem. So we consider a very general option market where all kinds of indivisible atoms will be sold to a finite number of bidders. So those goods can be identical, can be heterogeneous, can be substitutes or compromise, or any kind of mixtures of substitutes and compromise. And every bidder might demand a several number of atoms. And what is important is that every bidder actually has his private evaluation and every bundle of his interest atoms and can be strategic. So this means that he might manipulate his bid. And the seller also has a reserve price for every bundle of goods. Now the question is that we want to know whether it's possible or how to design a dynamic auction mechanism with simple and also probably practical and transparent rules that will allocate atoms efficiently, at the same time induce bidders to act honestly, and also require as little information as possible from bidder so that we can protect the private information as much as possible. That's the general question we want to address. Okay, so this option problem is actually a particular instance of the famous Hayek's problem, what they call the rational economic order problem. So maybe let me briefly quote some part of his.
Sorry.
Yeah, sure.
Quick question on the previous slide.
Yeah, sure.
So regarding the last point on the private information,
yeah,
are you worried about the information that is revealed to other participants or to the auction?
Yeah, also other people, so, any other people, of course, in particular to the seller. Yeah. Yeah.
Because there could be influence.
Yeah, I mean,
it's given only to the auctioneer, but not revealed to others.
So basically, you can, in particular, if you are seller, I'm the bidder. So I don't want to reveal my reservation value to you. So that is the key point. Okay. Okay. So as probably many of you know, in his famous AER paper, Hayek made this famous statement. So here I quote some part of his paper. So what he says that the peculiar character of the problem of a rational economic order is determined precisely by the fact that the knowledge of the circumstance of which we must make use never exists in a concentrated or integrated form, but solely as the disposed bits of incomplete and sometimes frank contradictory knowledge, which all the separate individual poses. And to put it briefly, it's a problem of the utilization of the knowledge, which is not given to anyone in its totality. And then he states the importance of prices. And actually, he also made this very important statement about the importance of price mechanism. So this price mechanism would have been acclaimed as one of the greatest triumphs of the human mind. So in some sense, he has had very, very deep insights about markets, in particular prices.
So which article is it? The use of knowledge?
It's an AER paper, American Economic Review.
Did he mention that price is the most?
Yeah, this is
It doesn't say that. Does he talk about the incentive compatibility of market mechanism?
No, he didn't.
So price is the most efficient way of.
Yeah, this is the message.
Okay.
Yeah,
So
but he didn't talk about say like Horwich about incentive compatibility. Yeah, in this paper he did, but he mentioned that the private, the incomplete information is extremely important for economic analysis. Yeah. Okay. So the takeaway of this lecture is, so here, so we present a universal dynamic auction design, and this dynamic auction design applies to all unimodal demand types are bordering and clumpering. This is actually a necessary sufficient condition for the existence of a competitive equilibrium and can accommodate all kinds of indivisible agents.
Well, necessary part is an overstatement.
Yes.
It is very particular sense. To dress up, it looks like a necessary part. No, very particular sense.
So I should probably, I already mentioned to some people, actually this is, they consider a regular economy because there are some other irregular economy which can also have a competitive equilibrium, but does not satisfy this condition. So what we mean by a regular economy, so you consider an economy, if this economy has equilibrium, then you delete any bidders or you delete any number of items, then this economy should still have a competitive equilibrium. So they actually consider such economy, what I should call a regular economy. So like growth substitutions. So you delete any number of bidders or delete any number of items, the growth substitutes still hold. So this
is defined in terms of demand types. And the demand types is the property of edge vector of the
yes.
The image of the demand correspondence.
Yeah.
And it doesn't say that at which price the consumers have multiple of them. It only talks about the edge vectors.
Yes, that's right. But he also actually, they also have another condition which is defined by demand type, demand sets.
Okay.
So they have a kind of a generalization of a so-called single improvement. So the probably that result in the paper, people might not pay much attention to that statement. Yeah.
Sorry, I'm not familiar as you guys on this nature of the necessity. So, so my recollection is that the necessity part is formalized in such a way that if anyone's utility function, so like it's profile of the demands, can be derived from this the demand types.
Yeah.
But then the equilibrium. So that is a sense in which it's very strong formulation of necessity. Is your comment on this regularity related to that, or is that separately?
Yeah, it's related. So basically, I think even mathematically, this statement is true. But just in the paper, they did not explain in such a way that it should, in some way, should make it very clear that there are economies in which equilibrium still exists, however, does not satisfy this condition. So the statement mathematically is correct, because this actually there's the underlying statement that it's a regular economy that, as I said, that for the same condition, if you delete any number of bidders or delete any number of atoms, that the sub-economy still has competitive equilibrium. So this is actually the very important. Yeah, sure.
I did not follow this. I don't know if you guys talked about it before, but I didn't. But isn't it similar to just say, instead of deleting bidders, can't you just say that they have like valuations that are very, you can keep the same number of bidders and just impose that they have like valuations that are extremely low, so that in effect they are completely irrelevant, or keep the same number of bidders.
Yeah. That's fine. This does not affect the statement.
Right.
Yeah.
So I guess the fact that you have to consider a subset of bidders, it seems to me less important than just allowing for, you could have the same number of bidders.
Here, my statement is that because some people might feel that the statement, the theorem is overstated, but actually mathematically it's perfectly correct, not wrong. However, there's some statement which you have to understand the content. If you don't,
mathematically correct.
Yeah.
Because necessity is defined in terms of demand types. I'm not talking about this theorem is wrong.
Yeah.
But this sufficient condition, the necessary condition part, is a very particular sense.
Yeah. You're right. Yeah. So here, in some sense, I have to clarify where actually the theorems are applied. Yeah. Okay. So here, so what is extremely important is that before this paper, actually there's a general belief that equilibrium could only exist for substitutes, mostly just substitute. What they found is that actually there are more classes of complements than substitutes under which you have a competitive equilibrium. So this is something quite surprising. So later on, I will show you.
We studied this paper and we are puzzled by this statement.
Oh, okay.
So what's the precise meaning of more classes?
Yeah, so I will come to that.
Okay.
Yeah. So this is actually quite surprising discovery, and I will explain to you later, just almost immediately. Okay, so let's look at the precise model. So we have n indivisible atoms, and actually we can also describe in a general form, just integer vectors, but the description we can easily extend it to that more general formality. Okay, so now every bidder has a utility function, and some bundle may not be acceptable. So here you see we have a minus infinity. This means those atoms will not be acceptable. Okay, also seller has a reserve price, and so we allow the possibility maybe some bidder does not want to have his, some seller might not want to have his own atom at all. So we also allow this. So here we have with this domain, so any atoms whose value is absolute above minus infinity is finite, then we call this effective domain. And anything whose value is minus infinity, then it's unacceptable. Okay, so we allow such a possibility. Okay, and here we use this this notation to represent the economy.
So
Yeah, sorry.
the supply of each item is 1. So
Yeah.
if you have 5 identical apples,
It's okay.
you treat apple 1 and apple 2 are different.
Yeah, yeah.
Okay,
Yeah,
but later-
but we can also immediately just take a 5 as
I know.
yeah.
So anything can be formulated.
Yeah.
But later, if you design auction,
And this doesn't
maybe,
matter.
maybe so if Apple 1, 2, 3 are identical for all consumers, the prices of Apple 1, 2, 3 move simultaneously.
Yeah.
So that's what you do.
Yeah, yeah,
Okay.
yeah. Okay, so here, so we use a linear anonymous pricing rule. So namely, just we give every item a price, and that price is the same for everyone. Okay, then demand set you already know. But here there's a little trick. Actually, the seller's revenue maximization is equivalent to like just a demand set. So why it can be done? So here, if you look at the formula, so I use a D0 P to denote the demand set of the seller. So you see here, this is what the seller tries to keep, and then this is the the payments for those items which have been sold.
Okay.
Yeah.
So the same argument shows that you can assume that endowment supply of goods are owned by lots of people,
Yes,
and
Yeah.
then demand analysis doesn't change because
you're right.
because of the
Yeah.
same reason.
Yeah. So in some sense, because here we assume that everyone has has no budget budget constraint.
Right.
Therefore, you can just treat all as bidders. But one thing we need to assume that if you are seller, then you are honest. Yeah, that's why it's quite important. Okay. Okay, so then allocation, just the distribution of atoms among all agents, including the seller. Okay, so here we have a D0. So 0 is 0 represents the seller. So then we have this one. Okay, then a allocation is feasible if every bundle xj is in his effective domain. So it means that the bundle assigned to each agent should be acceptable to the agent. Okay. Okay, now efficient allocation, which achieves the highest market value. So we use this SV, the market value. Okay, then we have a competitive equilibrium or variation equilibrium. This is what you already know.
One technical question.
Yeah.
So price could be negative and the
Yeah,
goods can be bad.
Yeah, yeah. So this here, so you see, we actually did not restrict the value. So here, just integer value. That's enough. Okay. So here, for the linear utilities and the low budget constraints here, so every agent has a limited budget enough amount of budget so that she's not subject to any budget or liquidity constraint. And when an atom is sold with a negative price, this means the seller will pay the price and the atom can be backed. And we have to assume that the market has at least one feasible allocation. And this assumption is actually very, very, very minimal. So it includes such possibility that the seller might not want to keep any of his her atom, but she's willing to pay some price to get rid of her items. So it means free disposal is not imposed here. Okay. Okay, now we look at a typical but a special market. Normally in the auction literature, you typically encounter such markets. So okay, the effect domain of every bidder contains at least one bundle of real atoms, and then you have a option not to choose any atom. So just you have a 0 and a non-zero vector in your effective domain. Okay, then for the seller, so any bundle of goods which is not sold, then the seller just keeps it. So that's so the effective domain is equal to the entire set of bundles. Okay, so in this one market, obviously there's at least one more than one feasible allocation. Okay, so what will be the major assumption on the economy? So we have a integer private values. So every bidder knows his utility privately and it can be strategically. The seller also knows her own utility privately and is honest.
Sorry, there's one question.
Yeah.
So here you assume that the range of utility function is always integer.
Yes.
So it never takes minus infinity, right?
Yeah.
So what?
Oh, no, here, sorry.
Possibly minus infinity.
Yeah, but answer here. Yeah, this is a mistake. Sorry. Okay, then the second condition. So actually this is a crucial condition that all agents have the same unimodular demand type. And this information actually for auction design, we need this information, the auctioneer. The designer actually needs this information. Okay, now we will let's look at what will be this condition. I think so some of you already knew this condition. Okay, I use this notation in demand set, and then I follow border one company. So we have the leap calligraph TU. So it's a set of prices at which there are at least two optimal bundles. So this what is it called? The locus of indifference prices. And so this basically this set basically concerns those prices at which you have at least two optimal bundles. Okay, then we need to introduce just one mathematical concept. So a set is a polyhedral if it's the set of points which satisfy a linear inequality systems. Okay, if this set is bounded, then we call it's a polytop. Okay, now let's. So then we in the paper they also call a facet. Some one concept is used in the paper. A facet of a polyhedron of dimension n is a face which has one dimension lower than the polyhedron. So okay, so then you can see the set the leap is actually the union of n-dimensional actually linear pieces. You cannot mathematically you cannot call it a facet because this is not precise, but the linear pieces are more precise. So these facets actually separate the unique demand regions. So in each of which some bundle is the unique demand. Okay, then we also use the normal vector for a facet is a vector which is particular to this facet at a relatively interior point of f. Okay, then a non-zero integer vector is primitive if the greatest common divisor of its coordinate is 1. So now we can introduce the concept of a very important concept of Baldwin Klumpery demand type. So a finite set D of non-zero primitive integer vectors is a demand type. If V is in set, then minus V should be also in the set. Then one more important condition is that every facet of the leap should have a normal vector in the set D. Okay, this appears abstract. Now I can immediately give you some picture to explain. So this is a blue. So this rectangular, so the blue lines all are facets of this rectangular. And this yellow, you have this triangle. So that these three yellow lines are the facets of the triangle. And the 4 blue lines are the facets of the rectangular. So one-dimensional. Okay. Okay, this is just a mathematical definition. Now, so here, you see the demand types actually do not reveal your valuations, but this captures actually the quantity essential and also natural attributes of the commodities. So in some sense, everyone will use tables as table, but our values on the table could be different. This is in some sense, this demand types captures that essential feature. Okay, then a square matrix is a unimodular if all elements are integer and its determinant is equal to 1 or minus 1. Or we also have another one. A matrix is totally unimodular if every minor of the matrix is 0 or plus 1 minus 1. Then a set of n integer vectors in the n-dimensional space is a unimodular basis if the square matrix of order n, which has the n integer vectors as its columns, is unimodular. Then what Baldwin Cromberry defined for unimodular demand type is that a demand type is unimodular if every linearly independent subset of the set D can be extended to a unimodular basis. So this is the definition.
So in this definition, where did you use the definition of total unimodularity?
Just for the typical and the special market, it has this property. But in general, we don't use to the unimodular. Yeah. Okay. So let's look at two simple examples. Then you might have a much better understanding of what are the demand types and what are unimodular demand types. So now here, so we have two atoms, two bidders. So you see the first example. So basically, you can see that both bidders regard both atoms as substitutes, and the values are different. However, both bidders will have the same demand type. This is actually unimodular demand type. Let's look at the next picture. Then you will have a more a better understanding. So look at this area. This area. So above 3 and above 4. So in this area, the bidder, the first bidder, so he will demand nothing. It's just 0. 0 is the unique demand bundle. Okay, in this area actually 1, 0 is the unique demand bundle. Okay, then this area is the, in this area, 1, 0 is the unique demand bundle. And in this area, 1, 1, both atoms will be demand and it's a unique bundle. Okay, what is this red line? So what is it called? This actually is a linear pieces, and Baldwin Cromberry also call them facets. Okay, this. Now, what is the demand type? Demand type is just the normal factors. This one, the normal factor. So this is perpendicular to this facet, this blue dash line, right? And this blue dash, and this, okay, this blue dash is the same as this one, so I don't repeat it. So then we take the union. You see this has a plus and minus two direction, right? So this also has two direction. This also has two direction. So you see, these vectors are essential, and for agent, for this agent, that blue dash lines will be the same. So in the sense that this demand type captures the essential feature of the goods. Okay, let's look at a different example, how demand type will change. So here we have still two atoms, and we have three bidders and the seller. So now you see the values. Okay, the values. So all agents regard atoms as complements. Actually, they all share the same unimodular demand type. This plus minus 1 0 0 1 1 1. Okay, let's look at the picture. You see here. So in this area, 0 0 is the unique demand, and this area 0 1 is a unique demand, and this area 1 0 is unique demand, and this area is 1 1. So here you see this dash blue line, blue dash line, 1 0, and 0 1, and this one blue dash line 1 1. Yeah.
It's okay for some agents to have a subset of this. So for example, suppose you have an agent who is completely indifferent, just a value of 0.
Yeah.
Would that be okay?
Yeah, it should. It's okay, but because that said, so you maybe just contain part of your information, right? That's okay. Yeah. So now here, actually, if you look at this definition, in particular, this one, every linearly independent subset can be extended to a unimodal basis. So this gives quite a lot of space, but also gives you an impression that it might not be so easy to verify. So actually, Fujiki and I, we discovered a new characterization of this unimodal demand types, which is much easier to verify. So here, so every unimodal demand type in n-dimensional space can be added with less than n new vector, so that the enlarged set is still a unimodal demand type and contains at least one basis. Okay, so actually in our paper, we need to use this proposition in our option design by assuming that actually every unimodal demand type spans the space. So in other words, yeah.
What's the difference between this and the definition which says it can be extended to?
So
I can't really,
yeah.
can't really read this English.
Okay,
So
okay, yeah,
you
yeah.
have demand
Let me.
and
So it's possible that the demand type might not have n vectors.
Right, then
Yeah.
it should be extended. That's the.
Yeah.
And what your proposition say?
The
In
proposition
that case.
says, if you don't have
Enough.
Enough,
compromise.
yeah.
And what does your proposition say?
so if you don't have enough n vectors, you can add someone, add a few new vectors so that the enlarged one still unimodular demand type.
Also, other unimodular consumers.
So actually, it still represents the same demand type, but now this is you have at least n vectors, and this set contains at least one unimodal matrix.
Okay, so suppose we have 10 commodities.
Yeah,
And 7 consumers.
yeah,
So they have demand type.
yeah.
And I'm sorry. So okay, so you don't have enough consumers, so that you have set of vectors, and the number of vectors is less than 10. So you cannot form 10 by 10 matrix. And
Yeah.
then what do you add?
So we construct a new matrix which have the original ones
Yeah.
and add some new vectors. So because if you look at this definition,
This is the definition of
yeah.
unimodular. Okay, unimodular can be extended to unimodular basis.
Yeah,
So that says that if I don't have enough vectors in script D, I can add something.
Yeah.
So that the unimodularity.
yeah. But here, here you need to check every regular independent subset of D can be extended to. So in the sense that
I see.
the combination is very big, right?
I see.
Then you don't know how much I have to check.
I see.
So now we have a quite an easy one to.
Oh, I see. That's it. Okay.
You see the point, right?
No. Please continue.
Yeah. So you see now, actually we use this proposition and the all proof, then we can have a alternative characterization of unimodular demand type. So this one is very easy to check a unimodular demand type. There's a unimodal if and only if every k linear independent vectors from the set D can find n minus k vectors from the set that to form a unimodal matrix. So now I restricted the number of vectors. You don't need to check so many possibilities.
If script D has only one vector, what does it say?
So I extended. I can extend it.
So D has only one vector.
Yeah.
If you add those things,
that's enough.
Identical.
Yeah, that will be
So
enough.
the determinant is 0, violating the unimodular condition.
No, if I have say just one vector, right?
Yeah.
Then I add properly some new vectors, n minus 1 vectors, as long as the new one is
It should be from set script D.
Yes, but first I use this one.
And I'm asking about proportion.
Yeah. So this for this.
What happens if script D has one vector? It seems to be wrong.
No, first I use this one.
Yeah. So
if it's if anything is less than D, right? No, less than n. They add something from this one. So then this will be always true. So suppose what you said happens, D does not have enough vectors, right?
Yeah,
Less than
it's a singleton.
Yeah, singleton. then I use this.
What does proposition 2 say in that special case? Proposition 2.
Yeah. So I just argue.
Yeah.
I just argue that I can use this lemma, this proposition.
I'm not asking why proposition 2 is true. So what does proposition 2 say when D script D has only one vector?
Yeah. So I add the n minus one vector
From D, right?
yes, from D, but
So that
I can
vectors are identical.
no. I will. I think I understand what you mean. Yeah.
So proposition 2 may not be true.
Can I just say that if you have only one element in D, that proposition will hold trivially for OK greater than or equal to 2, because you never have two or more linearly independent vectors from D because you have only one. So since the premise is always false, the proposition is true. So you just have to check the case for K equals 1.
No, I think you have your point. So here, what we mean is that suppose D does not have, so just has one, right? Then we use this one to extend the.
I see. So
This
that's
is
what
this is what we.
So I understand that in the premise of proposition 2 is that this element type D has already had been sort of
Yes.
extended using the.
Yeah.
Oh, I see.
Yeah.
But only
Yeah.
that time.
I see.
Yeah. So this is why I have to state first this one using proposition one.
But I think it's true even if you don't impose it, because suppose that you have only one element. Then when you want to check proposition 2, you never have, say, for K equals 2, you never have two linearly independent vectors from the set D because there is only one. So there is nothing to check in this case.
No, but if you have one, we have
No, so you have to check it for K equals 1. And for K equals 1, you need n minus 1 vectors from the.
Yes. That's exactly what we mean. But
I see. So
but I think Michiro has a point.
okay. Sorry.
Yeah. So this is what we mean. We have to use this one. Yeah. Maybe I have to think this. Maybe we have to somehow rewrite this in a way which is which will make sense clear. Okay. Now let's look at three typical unimodular demand types. So actually, they identify number of unimodular demand types. So first one is the famous cross substitutes. So actually here, it's very easy. So every vector x in D has at most one, at most one minus one, no other non-zero entries. So as you might recall in my first lecture, when we introduced the M natural concave function, so over there you have plus one minus unit vectors, and now you have the difference between two different unit vectors. So that's precisely this one. Now for substitutes complements, so then we give a partition of the set N S1, S2. Here we need to be careful. So here every vector X has at the most two non-zero components of plus one or minus one, no other non-zero entries. So that if two non-zero components of X have the same sign, then one must be in S1, the other one must be in S2. So this means that they have the same sign. Precisely, it means that they are complementary to each other. Minus means you reduce one, and the other side also should reduce one. That's precisely the complement. And plus one, plus, so if you add one table, then you also add one chair. So that's the complement. And here you have when you have a plus minus in the same set, that's precisely the cross substitutes complement. Okay.
Can I say, make sure I understand?
Sure.
So when you say, so if I understand where demand type is defined for a set of vectors.
Yeah.
Usually, let's say, cross substitute is defined on a particular utility function or
Yes.
perhaps the associated demand.
Yeah.
Correspondence.
Yeah.
So when you say B is cross substitute, and that's in what sense are they the same? Is that it? And it's defined in a separate space. So can you clarify a little bit?
So in a sense, this is still, I mean, the underlying is still, you have a utility function, right?
Okay.
So then then you have this need.
The way that.
Yeah, exactly.
So the statement is that if the
Utility function.
utility function
Yeah.
satisfies case of the conditions,
Yeah.
then
That
all
is-
the vectors
Yeah.
create the way that
Yeah,
they
yeah.
forms a demand type D
Yes.
that is no substitute in this sense. And
Yeah.
Is it there's something which is like butter?
So this actually, in the paper, they did not say prove that this should be equivalent. I believe they are equivalent, but actually in the paper they did not discuss that issue. So, but I think this is the essence of cross substitutes. So here, actually, anything when for substitutes, if you want to have a say equilibrium, then this is the maximum. In a sense, this is the unique one. No other possibilities. This covers all possible of substitutes. In a sense, this is the maximum. Okay, then the unimodal complement. Now you have much more possibilities. Because here you see a unimodal demand type is unimodal complement. If every X in D implies either, so all components are 0 or 1, or 0 or -1. So here, there's no unique or maximum set D to capture this one. Even just consider three commodities, then for such matrix, you have a number of such matrix, not one matrix. So this is why that in the case of substitutes, there are much more possibilities, and there's no unique maximum, say, complement something. We cannot have such statement. But for substitutes, this is the unique one, and also the maximum one.
Yeah, so what's the definition of maximum something?
Oh, yeah, you cover everything. You cover everything.
What's the mathematical definition of maximality?
So basically, this set is the maximum for any substitutes. Then the set should be contained by this. Yeah, but this one, no.
Mhm.
So just to understand, so the last one allows, for example, the possibility where X has 3 ones, and so it means that you would want to go either you get nothing at all, or you need the 3 goods at the same time.
Yeah.
And-
Precisely. Yeah. That's okay. Okay, then we have we have a structure. Yeah, sorry.
Sorry, so I believe I get the idea that intuitively the unimodular complements maybe have a maybe is bigger than those substitutes, for example. In terms of this
the number of such, yeah, that's right.
Are they also related to, let's say, other ways to other notions of like how big the subset of demands that satisfies this condition is. So, for example, one possibility may be to use something like the look at any maybe let's think the set of possible variation, spatial variation. So you may countermeasure of the utilities on some space, or so in the discrete domain without price, for example, one could use the way that Federico Jenkins, for example, counter class or choice rules by assuming that any subset could be equally like it could be chosen from the given set. So I guess sorry, I'm being very vague in this question.
Yeah. So here, maybe I just so for this one, I also have to point out, like in our second lecture, that when all agents have super additivity utilities, this does not cover. So this condition does not cover super additivity. So if you want to have say a utility function that will satisfy this condition, then the first example one might try is about impose supermodularity, add some extra condition, because even supermodularity will not have a competitive equilibrium. So this means this will not be satisfied. You still need to impose some additional condition on supermodularity. This is what I can say.
I have a question. In the market design conference,
Yeah.
Ravi Jagadish-san
Yeah.
gave us complete characterization, interpretable characterization of all unimodular demand types.
Yeah.
And he said that after changing the basis of commodity space, the demand satisfies certain consistency condition. So I don't remember the detail, but does that mean that after changing the basis of commodity space, it reduces to one of those? So second one, by basis change, it can be reduced to the first one.
Yes.
So does it say that after changing the basis, it can be mapped into growth substitute case or unimodular complex? Do you remember that was
this one is quite essential. You cannot change it from here to this one, but it's possible.
I know.
The other one is okay.
No. Take any unimodular demand type. And if you change the basis of commodity space, so you have a new definition of commodities.
Yes.
And this modified transformed model is either growth substitute or unimodular complements. But that his characterization. Do you remember his?
I don't remember, but
okay.
So sorry. So
I should ask this to Ravi.
Yeah. So but basically. Out there, he did some operation. So basically, you still need to group some goods together in such a way. So this group and that group has have something in common. That's the essential one. And now, in the sense that bottom corporate, the condition is also. So, okay, everyone looks things in a similar way. That's the essential condition. Okay. Okay, so now, okay, now we have, indirect utility as so the maximize the subclass. Okay, now we have the proof function. Okay, this one we already encountered previously. Okay, now we have the first lemma. Actually, the proof function is a polyhedral convex function bounded from below, and then for the first theorem, we prove that the market model satisfies this one, and then the set of compatible equilibrium price vectors will form a non-empty integral polytope. This means that every extreme point of the polytope is integer. So this is a very nice characterization. Then the following results also we can get is that if the market satisfies the both substitutes, then the set of compatible equilibrium price vectors actually is a non-empty integral polytopes with a lattice structure, because the lattice might not be a polyhedral. So that we, okay, now we come to the dynamic option design. So as you see from, from this lemma, so basically the underlying principle is try to find a minimizer of the proof function. However, there's a problem because as the auctioneer, this involves the private information of every agent. So the auctioneer cannot get actually this information. So this is the first difficult or challenging. And so now what information we should use in order to extract enough information from the bidders. Okay, then the second one, okay, in optimization techniques, you try to minimize a nonlinear function. Typically, you use gradient that try to get the minimizer or maximizer of the function by repeatedly local search. So here, the local search also plays important role. So here, how we do the local search, and what is more here, we have to deal with all possible unimodal demand types. So we need to have a method which can uniformly apply to all unimodal demand types. So in some sense, we need to have a very general framework to handle this case. So the answer is simple. So we use prices and demand sets. So this is observable information. And then we need to introduce a new notion of search set. So we use this tool to get the dynamic option design. So a search set for a demand type is the collection of zero vector and all non-zero primitive integer vectors such that this is the inner product of this vector with any with some linearly independent vectors from the demand set. So this search set is denoted by the color graph S and D. Now look at the previous two examples. And so the two two bids have the same unimodular demand type, this one, and then we can easily recalculate its search set is this one. So you see, you increase the price of either atom, or you increase or decrease both atoms by the same amount. Okay, now for the complement case, you have as we already see previously, that you have this demand type, then the search set is, you see, decrease 1 or minus 1, then you decrease 1, but increase 1, or increase 1, decrease 1. So, but never do atoms, two atoms simultaneously by increase or decrease. So,
Sorry.
yeah.
One question. In example 1, could you explain why 1 is in the search set? So how do you choose one? Sorry, anyway, so which is one vector which is chosen as 0, 0? No.
Choose 1 minus 1, the last one.
So my question is in the search set, so 1 is included, right? Then I still don't understand the reason. Because if you multiply any vector 1, 0, 0, 1, 1, so the inner product is not equal to 0.
No, this one. You have,
Oh, I see. Okay.
Yeah.
Sorry, thank you. Sorry. I see.
okay. Okay, so now here, I think the basic idea, maybe this I can skip, we already have. Okay, then the first one, we have this proposition, 4. So this one is a quite important one. You see here, the principle, underlying principle is try to minimize the approach function, right? So for local search, so at current price PT, now I do local search in the search set, actually in the convex hole of the search set. By local search around me. However, this is not easy because this is a convex hole of the search set. Too big. But actually, we don't need to search the entire set of the convex hole. We only need to search the finite vectors of the demand set. So this is a big step. And from the proposition 4 and also its proof, then we can get another one. It's a corollary, and this corollary is quite useful. So you see, when you do the local search, actually at current price PT, now there's a vector optimal bundle which can minimize your payment. Actually, this vector, this optimal bundle will be still optimal bundle when you just change the price a little bit. And this is a quite important. Okay. Is this clear? So you see here, now currently you have a optimal bundle, and now you choose an optimal bundle which minimize the payment of the bidder J, and this optimal bundle will be still an optimal bundle when you change the price from 0 to 1. So just like if this is 1, just delta. So delta will be in your search set. So this is a very important information. Now look at the first the maximum amount. So this one. So just look at this maximum max amount. Now, if we write this expand this one, you have this one by definition. Okay, and now use the corollary one. Then we have this one xj. So xj is optimal at price pt, and this is also optimal at price p plus epsilon delta including 1. So then this one, so this term for every agent, so this indirect utility reduction is nothing but your minimum payment. So you see here, you change the price from PT to PT plus delta, and this change, this optimal change is precisely the optimal price at PT, which gives the minimum payment of the bidder.
Sorry,
Yeah.
I got lost a little bit. So does it mean, in terms of information, it means that you need to know DJP?
Yes.
Like the whole.
Yeah.
So, I mean, it is important to observe all of it.
Yes. That's right. Okay. So now from that one, you see that this original problem has reduced it to this observable information. You have a min and max. So you see there's a trade-off between the seller and also the bidders. So basically it means that every bidder tries to minimize his payment for any price change, and then the seller wants to have the price change which gives her the highest revenue. So there's a perfect compromise between the seller and the bidders. So this is a nice. Actually, I still think feel this is a beautiful transformation. So from unobservable information to observable information. This, okay. Now we also have another pretty important theorem. So actually, this search set is also an optimal test set. So for any on any market which satisfy condition A1 and A2, P star is a competitive price vector if only if at this P star that this is less than or equal to P star plus delta for every price change in the search set. Okay, so now we can have the auction. So the auction is very easy to describe. So initially, the auctioneer just announced any integer price vector P0, and then ask everyone to report his demand set, and then after collecting this information, the auctioneer just solve the optimal problem. So the previous slides, that Formula 4. Okay, if the zero vector is an optimal solution, then the auction stop. Otherwise, then the auctioneer will update price in such a way that repeat this one. So what we can show is that this auction will always find an integer compatible equal price vector in finite number of steps when bidders bid honestly. Okay, so this is the basic auction, and then we can also design based on this auction. We can also design a
Sorry,
sorry, maybe yeah.
it's gonna be heavy, so I'm still having lost here. So so which part of the argument so far use this assumption of the demand type to be unimodular, or
This is a very good question. So actually, theorem 1, we need that one. Also,
can you remind me what's your
the other one, for proposition 1, we also need to use this one.
sorry. So what are the theorem 1 that you?
Oh, the theorem is it's the polytope integral. That one we need to use that condition, and also this one. This we also need to use. Yeah, so actually for this lemma we have to use a number of quite important combinatorial results.
So in a very special case where each consumer consumes at most one element, that's Gale-Drummond-Sotomayor.
Yeah.
So the price adjustment first identifies over-demanded set, and your general procedure coincides with their procedure.
If I start from a very low price. Yeah. I think most. Maybe not the same, but it's almost the same. I let me put it in this way because I know Gustav Cat, the auction will coincide with demand Gale Sotomayor when when they apply to the.
So the choice of delta somehow corresponds to find over demand.
Yeah. I think almost the same, but probably some detail may not be precise. Yeah.
So there is something. So at some point you were saying, can you go to the main result?
Next one.
The theorem on.
Oh, sorry.
Yes.
Oh, you mean theorem 1?
Yes. No, sorry. I think theorem 3.
Oh, theorem 3. Okay. So here, maybe just come to Friedrich's point. So here we need to use that unimodular demand type. This one we need to use, and also theorem 3, or the proposition 4 we need to use, and also theorem 2. Okay, theorem 3, this one.
No, so actually it was related to.
Just theorem 1.
Yeah, theorem. So at some point, you said for gross substitutes only, you have the guarantee of exist. I forgot. You said something. It was only true for gross substitutes.
For the lattice.
Oh, that was for the lattice.
Yeah.
Okay. Yeah. So when you're not in this case, this result.
Yeah, this.
Okay. So it says that even though you don't have this structure, you can still.
Yes. Yeah, we don't have because in general, in particular, if you have a compromise case, then the structure of the competitive equivalence you don't know what is the structure. Yeah. Okay, so I think then we have maybe just a little bit time to explain the rough idea.
Can I ask you a quick question? So
Yeah.
that you know that everybody has complements, but you don't know exactly.
Yeah.
You don't know exactly the nature of the complementarity, right? So you don't know whether sometimes you have an X that is there's 3 values of 1 or something. So
Yeah.
So in this case, the set of potential search sets can be pretty large.
Yes.
So right, because it can be all these. So what would you do in this case?
I think probably you can still roughly, I mean, use this mechanism, but maybe you need to modify when you get more information. The search set you have to modify somehow when you get more information. Because
you can narrow down.
Yeah. So because I mean, at beginning, it's possible that you might not. I mean, the auctioneer might not know your demand type, right? That so in practice, typically you.
So I was wondering about this, but you have so this assumption means that everybody has the same demand type,
Yeah.
including the seller.
Yes.
And the seller is honest.
Yeah.
So in principle, you can ask the seller, what is your demand type?
Yeah,
and then you know exactly.
Yeah.
But the thing is that if you're in the case of complements, then the demand type can be in principle very large.
That's
so
true.
ideally you would want to still narrow it down.
Yeah. So here, I think first you get some idea from the seller, right? So roughly, okay, if you think that probably all people will have will treat this goods in a similar way, then maybe okay, I take this as a first step, as a search step, then gradually as the auction goes on, maybe we can update a little bit about the demand type. So that I think in practice, maybe we should use in that way. Not entirely that from beginning to the end use the same. In practice, probably it doesn't work. Yeah. Okay. So here, okay. So still we have to generate the VCG outcome. So basically, we already know from Green, Lafont, and Holmstrom that in the models with transferable utility, actually any strategic proof mechanism must generate the VCG outcome. So this we cannot avoid. And the good sense is that, but we can reach this outcome through dynamic auction design. So basically, still use the same idea. So actually you see this VCG direct mechanism already gives us enough information in the sense that we need to consider the origin market and then all other sub-markets. In each sub-market, you delete one, you drop one bidder. So this actually is the idea of our dynamic auction design. So as already mentioned that.
So this is similar to Osabel.
Yes, this of course our design and the paths are not the same, they're different. But in principle, this idea use this n+1 markets. This is the same. Yeah, because this we cannot get anything else because you have to generate VCG outcome. And when you generate VCG outcome, you have to use n+1 markets. So that's the idea. Okay, I think I only have a few minutes. So basically, maybe I just actually the auction is not difficult at all. So now the only thing change is that here, this demand type, demand set might not be your demand set anymore. You might manipulate. And so here, if they are honest, then this should be just the demand set. But otherwise, this could be different from the demand set.
So which auction is incentive compatible? The original one or also the version? You
This,
talk about
so now this,
Original.
no,
one auction for everybody.
we use the original one to construct a new mechanism.
Oh, I see.
Yeah.
Okay.
Yeah. So here for each supermarket, we use the original one, and now
This market, so you're talking about the Osawell idea?
oh yeah.
Oh, I see.
Yeah.
Okay.
Yeah. So now we have a N+1 markets.
Okay.
So all markets use the same basic dynamic option.
Mhm.
And now, so here what changes just here, people might or bidder might manipulate this one.
But if you do Osawell version,
Yeah.
the mapping from what you say and final outcome is the same as VCZ. So automatically it seems to be dominant strategy incentive compatible.
Yes. So see here I just want to explain what might change.
Yeah.
So when
But
people
in
ask,
the end, you are going to prove that
Yes.
it's exposed to Nash equilibrium.
profit relationship period.
But maybe if you just look at the mapping from what you say,
Yeah.
and finally what you get in your Osawell version of your auction,
Yeah.
the mapping is equal to VCZ. So it must be dominant strategy incentive compatible.
So that's true. So when people bid the sincerity, that's true. Yeah. So here, so actually, when bidders bid honestly, then this payment actually will be just equal to the VCG payment.
Mhm.
So here, this okay.
Yeah, but it could be that because it's a dynamic auction, so lots of people have multiple times to respond, so you cannot quite show the dominant setting.
Yeah. So here we have to be careful because when we talk about the exposed profit relationship, it means it will be optimal on equilibrium path and also off equilibrium path. So this is so here actually we can achieve exposed profit relationship equilibrium. So even if after the player knows the private information of his opponents. So this strategy for every player should be still optimal and on equilibrium and off equilibrium path. So here you see that for the demand gear Sotomayor, they can only achieve exposed Lash equilibrium because they can only do unequilibrium path. So anything off equilibrium path, then they cannot converge to the competitive equilibrium. So that's so currently for dynamic auction, so exposed profit relationship is the highest standard that you currently you can possibly achieve. So it's still very difficult if you want to get sincere bidding is a dominant strategy for all bidders. That's much more difficult. Okay, so what we can get is that okay when bidders bid sincerely, then this auction will converge to competitive equilibrium and also generate VCT outcome. Then the revenue for the seller is not less than her reserve price. And also, okay, sensory bidding already states is exposed perfect lash equivalent, then this option is also individually rational. Okay, just on time.
Okay, is there any comment or question? I have one very
Yeah, sure.
minor technical question.
Yeah.
So suppose the variations are integers.
Yeah,
Suppose equilibrium exists.
yeah,
But maybe demand types may not be unimodular.
yeah.
Then you cannot really prove that price is an integer.
Mm. Then
You
this is
extensively use unimodularity.
this is not easy problem.
Aha.
It might be you might still have integer
Aha.
price factor, but I'm not quite sure how to prove it.
Your proof extensively used unimodularity.
Yes, yes.
Oh, I see.
Yeah,
Okay.
yeah, yeah.
Thank you.
And also we have to use the new proposition that I had with physics sense. Yeah.
Okay.
Okay.
Any other question? Okay.
Okay. Thank you.